All right, hey everyone. My name is Ritesh, and I'm be leading this stream. And so this is our third and last stream for FTC programming. So we've been together for the past 3 weeks, hopefully, and yeah, it's been a fun ride. So yeah. So once again, who are we? STEMpump is a student-led initiative that teaches students the best of STEM technologies for free. We cover everything from programming to robotics, even game design. This is STEMpump Online, our online platform designed to teach our in-person classes online. So, anyone from around the world, if they're available, can just hop in and then, treat it like a normal class. So how does this camp work? So, if it's your first camp for some reason, each one of our camps, at least this one, each week builds off the one before it. So FTC programming was held the past 2 weeks, and then this was the third week, June 9th, in 3 to 5 CST. And so during the stream, feel free to ask questions in the chat. We're going to get around to answering them, and then we also have people in the chat that are willing to help you out as well. If you have more questions afterwards, feel free to reach out to us. And after looking through all the content that we've had, we actually have more content than we have for the time of this camp today. So if we don't finish anything today, we'll potentially make a video and post it to our YouTube channel. And we're also going to have it available on our website as soon as we can. So if you haven't attended or missed our previous camps, you can go to our YouTube channel by typing in this link right here. I'm going to paste it into the chat. And you can watch last week's FTC Programming 2 and then the first one, which is FTC Programming 1. If you have the STEMpump app, you can watch them directly through there as well. So here have been our overall camp topics for the past few weeks. So on our first meet, we did basics of Java. We went over op mode design, TeleOp design, and we went into a little bit of autonomous. Last week, we went into autonomous and made a linear op mode autonomous. We went over our 3 sensors, our touch, our color, and our distance sensor. And we talked a little bit about a dynamic workflow working with modular code with functions and objects. And we went a little bit into encoders, but we're going to go a lot more in today. Today, what we have planned for is Encoder Basics, Gyro Basics, and so we're going to kind of talk about how those things play together. And then we're going to talk about Vision Basics, and then we're going to go into version control. And then our last one that we probably won't have time for because it's such a big part, it takes literally 30, 40 minutes to go over, which is iterative op mode autonomous. So we'll probably make a video about this last topic, but we hope to get these few things done today. So before we actually get into any programming today, we're actually going to go over a review of what happened last week, so we kind of get back into the mood and then kind of talk about all the things that we've done. So we went over functions last week, and a function is a piece of code that is called by name. It can pass data to be operated on, known as the parameters, and can optionally return data, known as the return value. And this is helpful, especially when we're dealing with large quantities of code. So if you go to our Android Studio project, we can look inside our robot. And so right here, these two are both return functions, and this is a normal function. So this is our init function, and it allows us to initialize our robot hardware, which is hardware mapping, setting directions, setting our types of touch sensors, and then telemetry. And so it doesn't really return anything, it just does these steps for us. And so right here we have return functions. So this one returns either a true or false, returns a Boolean value. Remember, true or false, 0 or 1, yes or no. So if the touch sensor is pressed, it will return true. If not, it will return false. And we can actually look in our touch sensor file. We can just write robot.isTouched, because it's the name, and then tell it which touch sensor we want it to look for. So right here we use the back one, we use the front one, front, back, and back. And right here you can see we use robot init, and we fed it in 2 parameters, our hardware map and our telemetry, because this entire file is an op mode class, and our originally robot class wasn't. So it needs to be able to feed in those values in order to get them, especially right here. And so like I said, some examples of functions and op modes. In autonomous, we have movement, we have encoders, and we have our time-based and our gyro. and then we have hardware and mapping, and then we have vision. And so we're talking a little bit about vision functions today. And I just showed you the hardware mapping. We do gyro functions, encoder functions, and we did already time-based functions. In TeleOp, like I said, we have return values from sensors, so we can use our touch sensor for that. And just like that, we can also use our movement and our hardware and mapping. So simply, functions allow us to use less code and be able to manipulate more with less. It's very helpful so we can minimize errors and fix issues across a larger scale. It also allows our code to be cleaner and more readable. And so when we're talking about minimizing errors and fixing issues on a large scale, say you made an encoder program, it drives forward and it's controlled by one function, but all of a sudden you're seeing that that function, isn't working, something's wrong. But you have it implemented everywhere. You use it in one file, use it in another, use it in all these different places, but it's broken. So if you just edit the one function, then you know that all the other parts will just automatically update because they're all just linked back to the original source. And so yeah, it allows the code to be cleaner and more readable because we don't have to call, our hardware mapping every single file. Like this is all we did for our encoders so far, and it's all we're gonna have was like one more line of code to finish that out. So what's the point? The whole point is that we don't have to write repetitive code, and we can keep our code base to a low line and character count. So we'll ensure that everything is more organized and is easier to write. And so let's just go over some object creation that we went over last week. And like I said, you can always go to stempump.com/r/YT to watch last week's videos if you're still kind of confused over this topic. And so modular code comes from creating object files that we can use in our op modes. And so once again, we're going to come back to the definition of Java, what it's given a definition as. So the definition of Java is a general purpose programming language that is class-based, object-oriented, and designed to have as few implementation dependencies as possible. And so we talked about how it's class-based, object-oriented, and it's general purpose because we've been able to use it for a lot of different types of things, and in this case, robotics. In our first camp, we went over the basics of Java and how you could use that to make if-else statements and print text. So there's a lot of different uses. And so what is an object? An object has both states and behaviors. So an example, a car has states, color, type, brand, but it also has behaviors such as starting, stopping, and playing music. An object is an instance of a class. States are information that are unique to the object, while behaviors are more like actions of the object. Another example is a dog. Dogs have, colors, breeds, names, but they're all going to, bark, run, play with a tennis ball most of the time. And so that's kind of the behaviors compared to the states. And so an object is basically an instance of a class. So we made two classes. We made our robot class, and then we made our movement class. So inside our movement class, we have all these different functions that allow us different types of movement. And here are init and return functions, and then the set encoders one that we're going to go into a little bit more that we set up last week. And so if we go in here, we created a robot. We used the robot class to create an object named robot of type robot, and we used the movement class to create a movement object named move. So move equals new movement with feeding in our robot and the entire op mode. So then movement can have access to sleep and telemetry or what else we would like. So like I said, states are information that are unique to the object, while behaviors are more like actions of the object. And so I've been throwing around the word class. A class can be defined as a template or blueprint that describes the behavior or state that the object of its type supports. And this allows objects to manipulate the methods of a class. So like I said, we made two classes, robot and movement. And then we created the objects right here. And we're feeding in different information. Maybe you had a different robot class. Maybe you had one class designed just for TeleOp and another one designed just for autonomous in the weird instance that you may have. So rather than using this robot, we could always just, if it maybe extends this, which is, some other terminology, you can always just feed that into here. So it really depends on it, but it's super flexible when you start adding parameters into the constructor, which is this little thing, of your file. So you throw around the word methods and functions a lot, and they're basically the same, just with different names. Methods are functions for your classes, and it's involved with object-oriented programming. And then functions are just groups of reusable code that can be called anywhere. And while they are the same, it is super easy to get the terms mixed up. So our methods would be, in here, that's where our methods, and then anything, in a normal file, maybe here, or anywhere that we really did. I don't think we have any examples of functions in here, but we do have examples of methods. And today we're going to make some functions that are within their own files, regardless of the movement class and the robot class. So we're going to start talking about encoders, and we went over this last week, but it's always great to have a little bit of a review. So what are encoders? So inside each one of your motors, and we're going to use the rev, HD hex as an example, I think, or the core hex, whichever the big one is. Pretty sure it's HD. But inside the motor, there's a little magnet at the end, which connects to the shaft of the motor. And that's basically the encoder. And from this, we're able to return tick values from it. And we can also give it the amount of ticks we would like it to go through. So you can see, here's our motor. The encoder would be right here. You can take off the lid and actually adjust it. And so last season, there was an issue, and some of the rev motors like this had faulty encoder setups in them. So they were too far away or too close, because there's this little circle right here, and they were too close to that. So you want to make sure, if you're having issues with your encoders, to always kind of quote-unquote recalibrate them, I guess. So you would want to pop this bad boy open. You would see there's a magnet inside. And then if you want to slip a piece of paper, and so that's how much space should be. Like a slight piece of paper should be in and out without any force. And so you should just push down on the magnet until there's just enough room where a piece of paper could slide in and slide out with ease. I don't know if the compact version or the core hex had that same issue, but I did know it was an issue on any of the HD hex. And so you have to get your special black, white, red, blue cable to connect to your control hub or any other electronic brain of sorts to connect in. Otherwise, you have no access to any of the subcommands or functions or different methods and return values that you can use with encoders. So how do we program them? The concept of encoders is pretty easy to understand, but it's a lot more difficult to program. There's a lot of different ways people do it, and we've experimented with a lot, and we're going to kind of explain our favorite way to deal with it. But depending on your robot and your situation, you might need to tweak it towards your standard. So we're going to outline our steps. So before we program them, it is essential that we know how they work, and that's really important because, like I said, it's kind of difficult understanding them firsthand, but once you kind of get into it, it makes a lot more sense. So we have 5 steps. First, we want to tell the robot we want to use encoders. Okay, that's simple. We want to use encoders. Just listen to what I have to say. Step 2, we're going to give it a tick count value, and we're going to calculate this based on inches times ticks per inch. And we're going to figure out, the fastest way to figure that out, because there's another way to figure it out, but it requires a lot more math. And if you're not, that well versed in it, or you want to save time and just get into testing really soon, this is a good way to get it. Then we're going to give motors a power. And then it's going to run the power until, either a timer kicks it out for a backup or that it receives the ticks per inch. So we're going to wait till we're done running. So those motors are just going to run and run until either both of the motors are done going to their desired tick, or that they are, or that one. And it really depends on which way you want to use it. If you want to have more control, you do both. Less control, you can just do one, which is a lot easier, because then you can basically jurisdict it based on one motor rather than making sure that both of them are, stopped. And the one weird thing about having both of them stopped is that, say your left one is done, but your right one is, the encoders are miscalibrated, it's falling behind. So you're waiting for both of them. That means the other ones just keep running until they're both able to stop. So it's really weird. So you have to really experiment with that, and we're going to show you how to do that. And then afterwards, we're going to turn off the motors and run to position. And then you might be asking, wait, we already gave it a tick value in motors and wait till we're done. So run to position is actually different. And it's the same as quote unquote turning off the encoders for that set time. And we're going to kind of go over that, like I said. So these are pretty broad. They're not as specific as we'd like them to be, just so you can remember the steps. So step 1. This part's pretty easy. For example, we're going to be focusing on our 2-motor drive, but you can adapt it for other drivetrains just by, adding more motors maybe, or reconfiguring how this works. And so we're going to write robot.leftMotor.setMode, and we're going to set it the run mode that we want. And for this case, run using encoder. Do the same for our right motor. And I think we named them left drive and right drive, so that's a typo. Then we're going to give it a tick count value. That's our step 2. So finding the tick count value is specific for your robot. So there's not really a good way we can say, hey, use this value of 39 and hope it works. So when you're trying to find a good inch value that you want to test out and make sure that it's correct, a good way to just find a really quick value is we use a TeleOp that we made that we're going to share with you that allows us to track the ticks per inch. And so basically what that does is you'll be able to put your robot on the ground, maybe set up a ruler next to it, and then you'll be able to put your hands on the robot and just move it manually. And from there, you will be able to check on your driver station on the telemetry and basically get a reading value off of it. So it'll say, each wheel and show you the current position that they're at. So you'll start it at 0 and then go to the current position. And so if you want to go to that, you can go to this link, stempump.com/r/get-encoders. And so let me just actually go to that link really quickly. I didn't set it up here. So you go here. So we have, it's called Gimme Encoders. We have our robot class right here. We set something called zero power behavior.flow. And zero power behavior basically says when I'm not when my wheels are at a power of 0, what do? So most of the times you won't have them on float. They'd be set to something like, I forgot what the other one is, but there's another one. And basically what it is your robot stops. So when it's at 0 power, the wheels cannot move at all. It's basically firm solid. What float allows you to do is have a little bit of spin. And so this is completely different than the float variable type, which is like the decimal points and floating point. But this basically allows me to move the robot when it's at 0 power. So the wheels can still free spin, is basically what this means. Then right here we have our left given and our right given. And so robot.leftDrive.getCurrent position will allow us to return that value, and same with right drive current position. %. Load. Cool. So, like I said, this is linked to the GitHub page with the code for the gimme encoders.java file. And so our third step. The whole idea behind encoders is that they go the same distance on any power. This is why using encoders is more accurate than using time-based programs. So like I said last week, when we were talking about time-based programs, there's so many variables that can come into effect with it. weight, your wheel type, your chassis type. There are just so many things that can influence it. Battery is one of the biggest parts, though. So the analogy we said last week was, not even an analogy, just example, was you have a robot, you've been testing your time-based program on it, it was working perfectly on Saturday, and you're, feeling good about yourself, everything's working. And so you saw that the battery was around, 14 volts, and you said, oh, I don't need to charge it over the weekend. And you come back Monday or Tuesday, battery, you plug it in, battery's around 12, 11, and you run the program, and it's a lot slower than it was on Saturday. And so the issue behind that is, it's been some days, power has been lowered, you used it, and so the program is just slow now. So what you do is you speed up the program, right, at this 11 or 12 volts. And then you charge the battery overnight because you feel like, I should charge it, it's getting pretty low. And the next day you come back, plug in the battery, run the program, and now it's running too fast because your battery is back at 14 or 15 volts. So that's one of the major problems, because that just, is terrible that the battery is influencing your entire thing. The time really has no sense. But we're going to actually incorporate time a little bit into this program that we're working on with a timeout time. So you can be aware of the 30-second autonomous period you have. So you can say, either go 2 feet or wait for 2 seconds to go off. So it's a good backup to look at for. So to give power to motors, all we have to do is this. It is robot dot left motor or left drive dot set power math dot abs parentheses speed, and then robot dot right motor dot set power math dot abs speed. So there's a reason we took the absolute value of the power. So this ensures that no matter what, the power is always going to be a positive value. When you're using encoders, you never want to use negative power. If you want to drive backwards, or you go back, like you make any wheel just go reverse, you want to give a negative distance, so it takes away. So if we look back at this, So we're using the math class that is given through Java. We're using the ABS function, which is absolute value. And what absolute value does is you basically feed it in any number, and it automatically converts it to a positive number. So even if I put in -1 by accident, it would still turn to 1. So it's a good way to make sure that no matter what, you're not sending any negative value in. And this is actually a return function right here. We're sending in one value and we're returning the other. So after this, we have to make sure that power is only being given when the motors are busy and the op mode is active. So we do this by writing while op mode is active and robot.left motor is busy and robot.right motor is busy. So this is an example where as soon as one of the motors turns off, that entire part. So yeah, if one of the motors finishes, the other one is forced to finish because we use and. So inside the while loop, we're checking that the power only runs when the encoder ticks are met. So if you say we have to go 100 motor ticks on each of these, but this one's a little stalling behind, that one's going fine. So this is true automatically because our op mode is going to be active when we're running it. So that's true. So we're using and. So the only way that this can run is if this, inside the parentheses right here and here, is true. So if that's true and that's true, then cool, run. But as soon as this turns false, since there's an and right here, it turns the entire condition false. And since this is true and that's false, and we're using and, it shuts down the entire while loop and breaks out of it. If this was an or, like with the vertical lines, then it wouldn't matter. And it would just be like, oh, if one or the other. You don't want to put an or right here, because then this will run forever, because the op mode is active is basically true the entire time. However, you would be fine to put an or right here. Then you can say when left is finished or right is finished. And so it'll be true no matter what. So while left is running, cool, it's true, or right is running. And so they'll continue until both of them are off. So this is probably the better option to make sure that one motor basically is kind of jurisdicting it all. So like one motor finishes early, both of them are kind of forced to. So inside the while loop, we're going to be checking that the power only runs until the encoder ticks are met. And so our step 5, our last step, after this, we're going to set our power to 0, and we reset back to run using encoders. And so right here, we run using encoder, run using encoder. This basically turns off our encoders and saying, cool, we're not going to use this anymore, we're going to rerun back. And so now we're going to combine all of our steps into a method that allows us to drive our robot using encoders. Okay. So we go to our file. So inside our robot file, we created a set encoders function. So all you have to do is, let's just rewrite this, I guess, just for people that weren't there last time. So public void set encoders, I spelled that wrong. And we're going to set left drive dot, so we can grab the method out of it, set mode, and the DC motor, we're going to grab the variable. So dot run mode dot run using encoder. And we're going to do the same for the other one. So right drive dot set mode DC motor dot run mode dot run using encoder. And so what we're going to do is we're going to create, we can just delete that, that's fine. So we're going to create a new file, encoder auton. You don't have to repeat this if you already did it, but this is just for people that weren't there. So we're going to say autonomous. We're going to give it a name. We're just going to name it encoder or autonomous auton with encoders. So inside, we're going to create a robot object named robot equals new robot. Grab all that hardware. We're going to make a movement object named move equals new movement, and it requires a robot and an op mode. We're going to make a override, so then we can use our run out mode. So run mode robot.init hardware map telemetry. Oh, forgot to extend the linear op mode, that's why. There we go. Okay, and then we're going to just do wait for start. After this, we're just going to write, check something out here. Cool, you have a telemetry. Cool, so that's all we really need right there. And so right now, we're just going to add, a move.robot stop. And so what's going to happen is we're going to add our encoder function here. And that's all we really need right now. So we look at our movement file. Our robot stop was just setting power to 0. And you can take this, let's just simplify it one more time, move 0. And that happens because we created this first move, and then we started, overloading it, is what it's called. And overloading is when we add different parameters but keep the same name. So then, if we want to have one, so right, we have one power that controls both, 2 powers that control each, 2 powers that control each, and then time. And potentially you can just even, while we're at it, you don't really need to do this, but let's just do it because why not? Do double power long time. Remember, long is just a long version of integers. It can hold more information. We just do move power op mode dot sleep time. Like that, you just got a whole nother function created. Okay, so now let's actually start working on our encoder function. So right after this move at the bottom, we're going to create a new function called public void encoder drive. We're going to give it a few parameters: double speed, double left inches, double right inches, and something called double time out seconds. So first what we're going to do is we're going to make sure that our op mode is active like always. So if op mode is active, just so we know that that's true to begin with. Otherwise, don't even bother running this. And first, we're going to find our target position, figure out where it is. So how many ticks do we want to go forward? So if it's 10 inches, go, that distance. And then add that to where we currently are. So we're going to create int new left target. We're going to use an integer because ticks can't be done with decimals. It's either, it has to be a whole number. So new left target equals robot dot left drive dot get current position. We're going to semicolon right there for now. Int new right target equals robot dot right drive dot get current position. And so what we're going to need to do is we're going to need to calculate the ticks per inch. And so as a sample value, we're going to use 24.5. So right here we write double inch count equals 24.5. And so now with this, what we can do is we can add left inches. So we use our how many inches we want the left wheel to go times our inch count. And then we're going to do the same thing, right inches times inch count. But now we're getting an error. And why is that? because we're giving it a double. Because we have double right here, we're multiplying by a double. But we need to round. So what we're going to do is, in parentheses right before it, write the word int. And what this does is it basically rounds it, the value that we get from this operation, so right, inches times inch count, and if you just calculate it out, so if we did say 10 inches, right, we would get 245. But what if we did, 9 inches? Then we get 220.5. Well, how would we round that? We just round to 221 with our inch right here. Now, what we're going to do is we're going to set target positions for our drive. So it knows, okay, this is my target. So robot.left drive, that's set target position. And then what we're going to do is we're basically going to give it the value that we gave. Calculate from here. So we're going to give our left the new left target, robot.right drive.set target position, new right target. And so now we're going to turn on run to position. And now this basically says, okay, cool. So you gave me your target position. Now let's figure out the power and let's actually start doing our movement. So we're going to set left drive dot set mode DC motor dot run mode. We have all these options. The one with the lines crossed through them are old, so they don't want using them anymore. So we're just going to use run to position. We're going to do the same for the other drive motor. So DC motor dot run mode dot run to position. We have that. And so what we're going to do is we're going to use our robot.runtime. If you forgot what our runtime was, in our robot class, we created a variable called, or an object of elapsed time named runtime. And it's basically a timer. And this is what's going to control our timeout. So we're going to do runtime dot reset, so it goes like to 0. Then we're going to apply our speed. So robot.left drive set power math dot abs, and so you can see this one's like overloaded completely. They're all different. So we just do abs and speed robot dot right drive dot set power math dot abs speed. And so now we're going to be working on that really cool while loop. So we're going to make a while loop, just simple. And we're writing conditions. So while op mode dot op mode is active. So now we know it's fully true. So basically what this says, we're going to make it say is, we're going to say keep looping while we're still active. If there's time left, keep the motors running. However, if there's no time left, stop the motors as soon as possible. And we use isBusy to check that when each of them hit their target position, that they're going to stop, which is safer so that the robot ends motion as soon as possible. But if you want, like I said, both motors to continue, you want to change it to an or conditional. So we're going to say and robot.left drive.isBusy and robot.right drive.isBusy. And so if this one finishes, the entire thing ends. But if I change that, to an or, if this one finishes and that one's not done, it can still go on. But for now, we're changing that. And then finally, we're going to add our last conditional, robot.runtime.seconds. If it's less, while it's less than our timeout time. So say we set our timeout to 5 seconds, so that's the max time it can run. So as long as we're under that 5 seconds, and we can run our motors. So if it hits it under 5 seconds, the correct position, we're all good then. Otherwise, we're to stop. Just format that. It's a lot easier to read. So we're going to display some telemetry now. So op mode dot telemetry dot add data path 1 running to %7D. And like we said, this is one of our types of string formatting that you can look up online. And we're first going to use new left target, new right target. So it tells us, you know, this is where we want to go. Next, we're going to write telemetry add data path 2. So this is our current position towards that. So we're doing pretty much the same format. So running at 7D. And then this is me, robot dot left drive dot get current position, comma, robot dot right drive dot get current position. And then we're going to update our telemetry because with linear op modes you always need to. And so you can notice that this is another form of overloading. We're able to feed in more parameters but use the exact same name of our method, which was add data. It's really long. I'm just going to format that once again. And so after this, while that's running, it's just going to keep displaying telemetry. We're going to do a robot stop, so we end the power. And you might be asking, well, how come we're not running anything inside of here? So you actually can. If you want to do gyro control, you can add that inside of here, which is what we did last year. But running the power, if we turn on power here and we stop it here, since it's linear, this is going to run, basically blocking them from each other until this is over. So we have robot stop. And then once again, we're going to turn off set position because that basically says, okay, move. And we can do that by simply just doing robot.set encoder. Oh, encoders. Just going to change that. It's here. Always format it, it's good. And then we're just going to add, a quick brief pause between all our motion. So op mode.sleep, and remember this is 250 milliseconds. So 250 millisecond equals 0.25 of a second. And so just like that, we have our encoder drive. And so let's just overload that because we love overloading. And you can just do public void encoder drive double speed double inches double timeout S. And so why would I use this? Well, if you want to go forward or backwards, this is a lot easier so you can forget writing by one more value. So encoder drive, speed, inches, timeout S. And remember, if you guys have any questions, feel free to ask them in the chat. So, yeah. So how do we add this? So we're going to create some right here. So we're going to move that encoder drive, set up robot.power. Let's use a bunch of our different functions we made. Just like weird. So, that's going to work. We're going to get a value out of here, whatever it is. And we can, let's make that 40 or just 4. And move the encoder drive 0.5, 30, 10. That's probably way more value than I need to do, but it's okay. And so you can see he shows up. So what happens in Android Studio is that your parameter names will show up as long as you're entering a hard-coded value, which isn't connected to anything else. So this one won't show us speed unless I change it to 0.95 or any other value, then it shows it to us. So that's one of the cool parts versus onBot. In onBot, it doesn't tell you, so you always keep going, jumping between files all the time. So yeah, if you try this on your robot, hopefully it will work depending on your configuration and everything you have set up. If that was kind of too fast for you, you can always go to stempump.com/r/FTC. You can find all our videos. This one will be uploaded later tonight, and then these two are both right here. And then you can also, go to any of these. You can go to, our modular code or our encoder control, and it's pretty much the exact same thing, and it gives you some resources at the bottom. First has some pretty good resources available. If you go to this FTC robot controller, then external samples, you can find so many different things. This is a really good document because it gives a lot of notes on why everything works and how it does. Talks about their desired path, which was, using variables and all this. It's pretty similar to what we have. It's not the same. It works pretty well. So now we're going to combine, or we're going to do that. Now we're going to actually talk about gyro. So inside of the Rev, expansion, and control hubs, there's an IMU sensor. And using this sensor, we can retrieve many different values, such as z-axis data, which is rotation. This is extremely helpful to make perfect degree turns, as well as maintain in a heading. And so today we're going to talk about how to make turns and drive at different angles. So it's going to be really, really fun. And we're going to use the terms gyro and IMU pretty interchangeably. For this camp, it just seems like we should do that. There's a lot more complexity to how it goes, but we're just going to refer to them as the same thing for now. So if we look at the control hub, where's the gyro? Well, it's actually like right here in the space. So depending on where you place this, that's how well your robot's going to be. So what you would want for the best results is probably placing your control hub or expansion up in the middle of your robot. Because if you think about it, you want this to be at the center so it can understand all the rotational movements, versus if you put it on the outsides where it's a little bit harder to deal with. And so this is how z-axis rotation works. Your robot is operating on an x and y, y is going forward, x is left and right. And so that z-axis, this is a depth, but if we're looking at 2D, we don't really have that depth, so it's going to be folded back onto these two axes, and it's basically rotation. So if you move this way, we're going to go from 0 to 180, 0 and then 180, and then this way 0 back to either negative or positive 180, same with the other side. And so 360 would be 0 all the way 360, or negative 360 would bring it other way, or depending on how you have that configured. So how do we program to use our gyro? And so just like the encoders, we're going to outline our steps so we don't get confused when we start to program them. We have 5 steps for setting up our gyro. The first step is to initialize our gyro. So we can basically say, hey, we have our gyro, so start using it. Second, we're going to receive output of information from the gyro. So you're going to return, our z-axis, all the different types of information. We're going to use this information to determine direction and then influence that direction. Then we're going to create functions to simplify our workload, so we're not copying and pasting the same stuff over and over again and writing too much repetitiveness in our code. And then finally, we're going to adjust for best results, so you basically can calibrate it to how your robot basically works based on weight and all that. So step 1, we're going to initialize the gyro. So initializing the gyro is just as easy as adding any other firmware. The difference is that we need to also set the parameters of it. So if you look right here, we have public, B, and F055 IMU, and this is the type of IMU sensor that we have inside the control hub. And we're just going to, this is an object, just like our DC motor or servo, or elapsed time, all of that. So we're going to name it IMU. And then we're going to give it parameters, which is going to be a whole new object. So the parameters of this are going to make a new thing. And then we're going to receive an output. So we're going to have a while op mode is active, and we'll be able to track angular orientation, turn this value into a string, and then update our driver station. So if you try this code on your robot will move manually now. And then you're also going to receive telemetry updates with updated IMU values. And that's super helpful, because if you don't know which way is positive or negative, it's cool to see, if I turn my robot this way, where's it going to go? Or you can also use this to basically see, what angle do you want your robot to go perfectly? And like I said, another good thing to do is to use the 0 power direction of float, so you can move your robot and then it'll be good. So then we're going to influence our gyro. We're going to force the robot to correct itself. We're going to create a new variable to control this x-axis. So you can basically say, okay, we're here, so now we can fix that. So this is helpful on mecanum drivetrains, because as we mentioned, they drift off course a little bit due to their slippery nature, because each one of the little rollers is angled, which basically means that your robot can't really, strafe properly or drive straight without curving just a little bit, unless your chassis is perfect and you figure out how to fix all that issues. Most of the time you probably haven't. So we're going to create a double named IMUZ, which is angles at first angle, which is basically a way of us to grab the value. And then we're going to add it to a move function, which is very simple. I think that we've already made. Yeah, we already made it. And from there, we're going to make it negated, and then we're going to multiply it by 0.02. And so just so you know, that's like 2%. So we're basically going to multiply that value by 2%. And you'd be like, oh, why do we want that? Because we don't want the robot to turn out of control. We want it to move just a little bit to recorrect for the angle that's being modified. So, next, so that loads. And then we can also create a value called bearing. Sorry. And so you can modify this 0.02 basically on how fast you want to recorrect the robot, but you have to realize that the higher value you make it, the more likely your robot is to, mess up a lot more. Because if you recorrect it, it'll start spinning out of control because the power is getting too high. And so what we're also going to do is rename our IMUZ to the word heading. And this is going to make a little bit more sense later. So we're now going to create a double type variable named bearing. And so we're going to be changing the heading our robot is facing from 0 to 60 degrees. So we're going to create a double named bearing that's going to be equal to 60 degrees. We have our heading named angles.first angle, and then move, and then 0.5, our bearing minus heading times 0.02. I am turtle to best, PID. We're not going to be talking about that today because it's a little bit more complex than a lot of people that signed up for this camp can, understand at the moment. But we're probably going to add it to our course curriculum later or make a video on it. So step 4, we're going to create functions. So by moving this into a function, we can make things a lot easier. So we can create, the object of angles inside here. We can add our heading, and then from here we can just, fix that and use our basic move function to basically control the move gyro and make it turn in different directions. And then step 5, we're going to adjust for best results. So you can do one more step further by adding time into this. So we added our time into our encoders just so it would have a backup, and we can do the exact same for this. So we can add an elapsed time, timer equals new elapsed time, timer.reset, and then while op mode is active. Pretty similar to what we did. That's typo right there. So now we're going to combine all of our steps into a method that allows us to control our robot using the gyro. So if you open up your robot class, we're going to add a new object, public bn 55 or bn0. We have this. Then we're going to, instead of init, we're actually going to start calibrating all of it. So we're going to create our parameters reference right here. Parameters equals just like that. Params dot mode. Sensor mode. Mu. Params dot angle unit equals bn dot angle unit degrees. Then we're going to create our acceleration unit. And you don't have to understand most of this right now. Just know you have to declare it. And then meters per second. So let's just clean this up a little bit. And let's just set our logging false. So we're going to create our hardware map. So hwmap.get, then bno, and then class, if we name it IMU. Then we're going to do IMU, initialize, and we're going to use our params. So let's kind of walk through this. We created our gyro object named IMU. Then we created a parameter set for it, and we set all of them. So this first one's just going to say the mode is going to be an IMU mode. We're going to be calculating things in terms of degrees, this is our acceleration, and meters per sec. We're going to turn off our logging. Then we hardware map our IMU. So hardware mapping an IMU is pretty easy. It should come up under your options for expansion hub most of the time, and as well as the control hub. And then we're going to say IMU.initialize using these parameters that we've set. And so right now from here, we have finished our first step. And so we're going to create a new file called Gyro Auton. We're going to create it in the autonomous. Name equals Gyro Auton. We're going to extend linear op mode, robot equals new robot. Let me set my override in. Op mode. Here we're going to create a movement. Move equals new movement. This, and it's pretty much most of our same old stuff. Robot.init, hardware map, and telemetry. Wait for start. Then we're checked while almost active, so this keeps looping through. And so right now is the part where you can basically going to start testing. So we create an object called orientation, and make sure it's this navigation one and not the drawable gradient drawable. Orientation angles equal with robot.imu. get angular orientation. So you can grab those values. Then we do telemetry.add data. Name it IMU output. And then what we're going to do is we're going to apply our angles. However, we need to convert it to string because of the type of object it is. So we're just going to type to string. Okay, so from here, like we know, update. And so if you run it like this, when you move your robot, you'll be able to see that it's responding to the movements manually. And like I said, you can always use, semicolon right there. You could always add the 0 power direction of float so you can move it. And so what is angular orientation? All it is just basically saying is, can you grab me the z-axis and all our angles from the robot's IMU? It's really all that is. Telemetry.update. So now we're actually going to comment this out. Actually, no, let's keep this top one, and we're going to leave those actually also as well. So we're going to create a double. IMU z equals angles dot first angle. And this is basically more of a degrees value that we can receive from it. So right, move 0, and then we're going to do negative z times 0.02. And it's like, what? That's weird. Move makes sense, yeah. So our left power and our right power, but we want to change that. We go back here. Movement is right here. So notice how this move is left and right power. What we want to focus on is a turning and a forward. So we're going to go into our gyro and create a function rather than using this method. So we can delete that. We can actually just change that to just a regular move. Public. We don't even need this in the end. That's useless. We don't need that. Public void move. Double forward. Double turn. And then robot.leftDrive.set power forward plus turn. It's very similar to when we programmed our two-wheel drivetrain. I think it was my first TeleOp L. Yeah, see, we used drive minus turn, drive plus turn. So we're going to do, and then robot.right.drive.set power minus turn, and depending on what you have, you can swap those. So now we have this. So we have 0 power, so let's just 0.5 it. So it's going to be moving forward at 50%, and if you move it if you hit it at the sides a little bit, it'll try and recorrect to its original position. If it's not trying to or moving too slowly to recorrect, you can always increase or decrease the 0.02 value and find what works perfectly for you. So this is really helpful on a robot like a 2-drive robot, because if you turn it, it's still facing forward. But on the mechanical robot, it's kind of weird because say you push it head on the side. Well, since it can strafe, as soon as you hit it, it's technically still maintaining that same direction it was facing, so it won't correct as much. However, if you turn it while it's facing the same correction, it will try and result back. So we have that. And so now we can kind of start reworking these. So we're going to rename IMUZ to heading. And we can replace that as well, so negative heading. And then next what we're going to do is we're actually going to, so this would do the exact same thing. So if we add another variable named bearing, So where we want to go, we'll set to 60, and we can just set it to bearing minus heading times 0.02. And basically we'll then have, our value. So 60 minus whatever we're at. So if we're at 0, 60 minus 0, then we're just going to, do our normal turn. It's going to turn to that if it wasn't already there. But say we're already at a value of 60. So 60 times 60 is 0.02. Boom. Still stays that it'll have 0 turn to it. So based on the angle that it is basically how it influences the drive. So we can actually take this a little bit further by converting this part into a function. So we can comment that out. Public. We can get rid of this. We don't need that. So orientation angles equals robot.imu.getAngularRotation double. I didn't even finish. Public void move G double forward double bearing. So rather than giving turn power, we're going to give a bearing degree. So double heading equals angles dot first angle move forward comma bearing minus heading times 0.02. Not 0.03, just 0.02. And just like that, we have a move G. So you can just write move G. Yeah, let's move 0.5 at 45 degrees. So now it's basically going to turn, if it's not at there already, it's going to turn and start going. So what we really recommend, starting off maybe at 0 or something, we go ahead and see, just goes forward. And right here in these instances, you'd have to set sleeps because nothing's stopping them. But we're not going to do that right now. And then we'd be at 0, drive straight, 0.5 maybe for 2 seconds, 1 second, whatever. Then you turn to the 45 and start driving straight there. And you set it to 90 and all that. So what we're going to do now is we're going to add time into it. So we're going to create public void move GT double forward double bearing double set. We're going to create an elapsed time named timer equaling new elapsed time. And then we're going to do timer.reset. We're going to do while op mode is active if timer.seconds is greater than sec. So if we go above, we're going to break. And so this is just shorthand conditional. So if this is true, do this. Otherwise, just move G. So G forward comma bearing. So if you now implement this, we can say, we should just have the 2 rows. And we'll say, 2 seconds, 2 seconds, boom, done. So we're going to do a quick review over our encoders and our gyro before moving on to vision today. So for our encoders, we created this method inside of robot class named setEncoders to basically run using encoder. Inside of our encoder auton, we would say, here's our 2 objects. We declared initialization. Here's both of our encoder moves. This one's overloaded, that one's not, and then we stop all power. in movement, we basically check first that we're running our up mode. We find our targeted position, so where we want to go. Then what we do is we set target positions, and we say, okay, run to this position. We reset our timer, and then we run using absolute value of power so that we're not using negative power. Then we're going to run our while loop, checking that our up mode is active, so that's true always during our up mode. Then making sure that at least one of these is busy, or both of them are busy. If one of them breaks, the entire loop ends. And we're also going to make sure that we're under our timeout seconds. Because if we go over, ends. If one of our motors stop, ends. And in the weird case that op mode active isn't active, ends. We're going to stop our power, set it to 0, turn off run to position by resetting run using encoders, and then we're going to sleep for 250 seconds, otherwise known as a quarter of a second, or 0.25 second, 250 milliseconds. For our gyro, we create a new object named IMU. It is a BN0055 IMU as the object name, just like DC motor, servo, digital channel, elapsed time, I like all of that. The hardware map's pretty much the same. We declare a parameters for it named params with all these different settings. One that says it's an IMU, degrees, the acceleration unit, which doesn't, you can mess with that if you want on your own time, but this is one we use. You have logging not enabled, and then we say, okay, initialize our IMU using these parameters we set up. Nothing else in here. In our gyro auton, we don't use our movement because we're going to be controlling it using something like this. And so watch what happens if I try copying and pasting that in. Let's just see. Automatically errors out because these two have the same number of parameters. If they have different names, it doesn't matter, but it matters with the number of parameters. I can add 100 parameters for all I could care, and it would still work with the same name of move. So that's why we stopped. We didn't even bother using our movement object. And our code was still pretty short. Initialize, we created a variable named angles, which is actually an object. Get the z-axis value for it. We declared it through telemetry to our driver station. We worked with bearings and headings to basically force it to go in a certain direction. We made this function with forward and turns, very similar to our drive TeleOp file. We created our move G, which just used gyro, and you would have to have sleeps afterwards, and we used move GT, which was designed to use time into that. So that was basically gyro and encoders. Now we're going to talk about object detection in Skystone. So during autonomous last season, your robot would need to the main object detection or vision in the game was detecting out of the 6 where the 2 Skystones were. And so then you're supposed to bring them across your bridge to receive points. And so the only way to receive those points is if they were, your first 2. So you can get 1 Skystone, get the points, get both, but they would have to be in the first 2 that you brought over. And so you might be asking how, if your team, didn't get vision going up. So there's a lot of options to choose from for object detection. We are going to be going over, TensorFlow and Vuforia. The great thing about this is that first gives sample code that's already been trained to start off, and the first step to getting object detection is to understand how the sample code works entirely. And so many students new to FTC usually get TensorFlow and Vuforia confused. Oh my god. And so we're going to define them right now. So TensorFlow is a machine learning library that allows us to differentiate between the stones using trained data. So every season, especially last season, first would basically be training a machine learning algorithm model, is what they call it, and it basically say, okay, this is a Skystone, this isn't a Skystone. Is this a Skystone? No, that's a Skystone. Basically training a model in a way that kind of thinks like the brain, which is machine learning, in order to differentiate between the stones. And then Vuforia is the way of opening our camera to scan and return back information. And so it basically knows, it can read the little pictures on these stones. And so for our method of vision, we'll be using both of these for the best results. And so we're going to get the sample code. Encoder Studio has the sample code in the external samples folder, and OnBot has it available as a template. And we're going to go over it in a little bit after a few of these slides. And so the first thing we really need to do is get a Vuforia license at the Vuforia developer panel. And you can get a code to run all of your sample programs. So you can go to stempump.com/r/Vuforia. And let's just copy that link. And it'll bring you to this page. And we could log in right now if we wanted to, but we're not going to. And basically from here, you can create a license key. And so usually what happens is that, these keys cost a lot of money the more you use them. But since your device never really connects to the internet or connects to their whole system, it never checks if it's being used, which is really cool about it. So you can go back to that link. Let me paste it. stempump.com/r/Vuforia. And make an account, grab your key, and then you'll be good to go. And so it can be obtained free of charge from the Vuforia developer website right here. So there are two types of sample files that are given, something like called normal or webcam. And the normal version is for teams that strictly use the expansion hub and the standalone RC, meaning the robot controller. So you want to use the integrated camera in there. And then the webcam version is basically forced for teams that use the control hub. But if you have an expansion hub, you can use it. And I would definitely recommend using the external camera if you can, using the webcam, because you give a lot more freedom, you have higher quality, and you're also not restricted by your size of the phone and where you place it in proximity to the expansion hub. The camera we used this year was the Logitech C720, and it worked really well. It's a pretty nice camera. You've got to mount it somewhere safe on your robot, and it's good to go. So we're going to talk about where to put this later, but a few lines down, we're going to find an area like this. And so you're going to want to paste the key you got from Vuforia there. And so if you run the program, you're going to see that the phone starts to recognize if each object is either a sky stone or a stone. It also is going to tell you the left, top, and right bottom coordinates on the XY plane for every object seen, but it won't be able to distinguish the position of the stone. And we're going to talk about more about this later. Last year's code was the first year that really did like a big object detection thing for Rover Ruckus, and then they And they basically also had the positioning software within it, already had the code to position and all of that. So, but this year they got rid of it, and so there's a lot of things you could possibly do now. So, like I said, Rover Ruckus first was kind enough to give the code to find the position of gold mineral, but now all we do is we get these different coordinates from the camera. And so as of the 5.2 update in Skystone, there was a bug in the code. I don't think it's been fixed yet, and I don't think they're planning on fixing it even in 5.4. But you have to add a I++ to a loop, and basically this allows it to differentiate a lot better by completing the loop that it goes through, rather than treating every object as the same. And so there's 4 really big ways that you can find positioning of these stones. The first one is 1/3 random chance. You have a 1/3 chance picking the right stone out of the 3. And that might work well for you. You might be just like saying, okay, cool, I'll take the 1/3 chance. It's better than a 0% chance, and that's true. But you should really look at the other options. The next one would be using last year's code. At the beginning of the season, I tried last year's code, and it worked perfectly if you just replace some of the variable names. But it's not good. It really isn't as good as you would want it to be. The third option is using external tools or custom solution, maybe using Doge CV, or just any of those other types of options available to you. Or going, custom TensorFlow Vuforia model. Or you can use the given information and make a solution from that, which is the method that we're going to be going with today. So how can we find positioning? We can be doing that by using option 4, using the information given and finding a solution from that. So if you run the code, the camera places boxes around each object it sees, regardless of being a sky stone or a regular stone. And then the way it basically differentiates them is using something called labels. And you can basically figure out what the label of something is using recognition.getLabel. And what we're going to do is we're going to check that recognition.getLabel is equal to skystone. And so we can basically use variables to figure out, okay, cool, is this equal to skystone? No? Cool, then I'm not looking for that one. From what next? So from here we can do a lot of different things. And the way that we decided to approach it was to find the midpoint, the horizontal midpoint of the skystone. Using basic geometry, it's like super easy. It's just averaging and finding midpoints. You can find the horizontal midpoint by adding the left, right, x values and finding the average. To find the vertical, you'd use the top and bottom values. Determining positioning. And so the final step would be determining the positioning based on this midpoint value. But this is the hardest depending on which position you're in. We just use simple trial and error. The camera output is an X and Y grid. It's a 2D grid, and each pixel has its own coordinate. So 0, 0, 0, 1, 50, 60. So what you need to do is you need to check the position of your code with nested if statements to see if your horizontal and or vertical midpoints are within a certain range. As every round, your midpoint might change little by little depending on how the stones are set up. So you need to make sure you allow a big enough amount of variation or range. And so what we're going to do is we're going to create something called invisible rectangles. And they're basically going to map a plane, 2D plane, over our object, and they're constantly check if any of the midpoint coordinates fall in that rectangle. Our ranges vary around 50 to 150 pixels, just to show the scale. If you use one of the midpoints, you'll be 85% accurate, but the last 15% is cemented by that vertical midpoint that we talked about. However, the only way to really use the vertical midpoint is if you're guaranteed that your camera is fixed in a position where it will always, see the vertical height of the skystones every time. The horizontal height is usually always going to be the same from where you place your robot, but the vertical height might change if it's, mounted weirdly. From there, you can add telemetry to show if position's been found. This is one of the more effective and simpler ways to use object detection, which I said is like calculated by basic geometry, just finding midpoints. And so here's a visualization picture we have. We have our skystone right here. We're given this red circle right here and this bottom right bottom. And so we can find something called mid-H and mid-V right here in this blue circle. So we can take left plus right, divide by 2, and then find the middle point. So right there. It could be anywhere on there. But then we can use our mid-V, so top plus bottom divide it by 2, and then find that point that meets exactly in the middle. And then we have something called the invisible rectangle, like we mentioned. And so this can be a value that you can find trial and error. And we're going to kind of give us some examples of this value. So, you might want to, what we did is we tried to figure out how to make it big. First, we really focused when this image was made on the small portion, but it's a lot better to focus on a larger area, because then you're sure that there's a lot more, even if there's a little bit of slight variance, you know where it is. So now we're going to take all of these concepts and apply them via code. So we're going to take, if you go into your FTC robot controller, open it, go to Java, external samples, and you find this concept TensorFlow object detection. What we're basically going to do is we're going to copy everything except the package at the top. I'm going to create a new file inside here. Sky. Just going to paste it so we keep that package. And we're going to version. And there's a lot of comments here that we're going to kind of read through a little bit. Well, I'm not going to input our key today because it's just so long, but this is where you would want to put it right there. So we're just going to add some random. Okay, cool. So this disabled that tag, we haven't talked about that yet, but basically what it does is it basically says, should I show this to you on the phone or not? So basically, if you have this disabled, which this is right now, it won't show up on your driver station to select. But if I just comment it out, then it will show up. And we want to change this from a TeleOp to autonomous. There. Let's just clean up a little bit of this. And let's just format that out. Okay, so what we're given first, we have 3 variables. So we have this, which is the asset name, so we can find the model, .tflight. This is our first element and our second element. Our second element is SkyStone, and this is the one we're focusing on. Here's some more information. If you want to find your code, here's the fake one I wrote in. We're going to create a object named Vuforia, Vuforia localizer named Vuforia. We're going to create an object detector for TensorFlow named TFOD. We're going to inside our run-out mode, we're going to initialize Vuforia. Then we're going to initialize TensorFlow if your device is compatible, and most legal devices in FTC are. And you don't have to worry about control hub because it definitely is. And so you basically say TFOD is not null. And so this basically initializes TFOD. So it says, okay, if there's something in there, if it's activated, which is right here, if it's initialized, then we're going to activate it. And then, same old, wait for start. So we're going to say if alt mode is active, so make sure it's true. While alt mode is active, we're going to make sure that we're looping first. If it's not equal to null, cool. We're going to create a list right here, or say if updated list is not equal to null. So if we see something, and then we're going to start printing out data right here. And so let's just add in our little fix. So I++, just so it loops through, because it's going to reprint I right here every time. And then we close it if TFOD is still not equal to null when alt mode is not active, shut down. Right here is where we initialize Vuforia with our webcam. And if you have a different webcam name, you can change it right here. It's as simple as a hardware map. And right here is where we initialize our TensorFlow. And so right here, one of the bigger parts right here is the minimum confidence. And so how TensorFlow works is it uses confidence levels basically to determine if something's a skystone. So it may be only certain that the thing it sees is 20%. It's only 20% confident that it sees a skystone. Then it won't call it a skystone. However, if it sees something that's like 85% confident it's a skystone, it will call it a skystone. So the lower the number, the more likely it is to call something a skystone. But at the same time, the more likely it is to make an error. And you don't want it making errors. So we like to keep it around a value of 0.75 to 0.9. Don't keep it too high, otherwise it'll only work in the senses of super perfect accuracy. So we can go all the way back up, and we'll start adding in some of our code. So hopefully you've already added in your Vuforia key. This one's fake, it won't work. It's a lot longer than that too. Right after here, we're going to create a string named position equals not found. Then you can delete some of these comments. I'll just delete some just for less code, less mess. You can always add your robot into it. Let's do that while we're at it. Okay, we're going to initialize our robot right here. And just like that, we already have all of our robot stuff in. So now we're going to actually figure out, okay, how do we differentiate each stone? So first, right off this I++, we're going to create a conditional. So say if the recognition that we're looking at, so this basically loops through all the recognitions, if the recognition that we're looking at, get label, is equal to label, you can use dot equals, label second element. And so normally what you would want to do is use an equals equals, and that might work here, but a lot better of a way when you're working with strings is to use dot equals. It's a lot. And so why do we write label second element? So that we can be sure that if this changed, we'll be fine regardless. And it probably won't, but it's just good to reuse some of our variables. So now we know anything that happens here, we're talking about the skystone. So now let's calculate our mid H and mid V values. So mid H, or double, mid-h equals recognition dot get left. This recognition get right. And so another way you can write this is you can write double mid-h equals, I should just uncomment that so you can click writing. Recognition dot get width divided by 2. I still have to divide by 2 up there. So that's just another way you can do it. This way is just a lot easier for people to understand. You can also do calculator mid v. Get top recognition dot get bottom divide by 2. And then another way to write that, double uppercase v mid v equals recognition dot get height. Fix some of that spacing. So we have 2 of our variables now calculated. Now using these, we can figure out, where things are. So first you can say, if mid-h is less than or equal to 225, position equals left. So we have, say we have all the way on here, we have like 1,000. Here we have, 0. We have 300, 300, so it's, 350-ish, whatever. Just dividing it into 3 parts, one being stone right here, one being stone right here, one being stone right here. So say 225 is like right there, and our midpoint is right here. So now we're saying, since our midpoint is less than this value, you must be to the left. Get it? Then what we're going to say, else if, so this is called an else if. So if this one's false, let's check for the next one. It's better than writing, multiple if statements in a row. What we're going to do is 225 greater than or equal to, or less than equal to, mid-h. So if this value is less than or equal to mid-h, and mid-h is less than or equal to 425, then position, and yeah, elif is the same as else if, equals center, and then else if 425 mid-h. We do position equals right. So we just break out here, right there. And we're going to add telemetry to add data, skystone position, position. So we have all this, and this will basically tell us where it is. And so you can do a lot of other things after this. You can do, maybe another if statement right outside here is what we did. We did like an if statement saying if timer 5 seconds are done, just go choose randomly, go for the middle one, just as a backup in case none of these work. And the reason we're going to use an else if right here rather than else is if it's an else, then it'll be like, okay, it doesn't meet those conditions, well then it must be on the right. But if it accidentally meets one of those conditions and it just misses, then that's not good. At least with this other way, we can keep checking over and over periodically. Okay, so so that's basically basic vision, and you can try that and it would work pretty well. You can always refine it a lot more than it currently is, but it's pretty good if you're want to explore that into next season, because there's definitely going to be a vision element towards it. So our last concept today is version control. We might end a little bit earlier today just because of we want it to fit some content in, and there's nothing that like really small to fit in left. So version control is a system that records changes to a file or a set of files over time so that you can recall specific versions later. Using version control also generally means that if you screw some things up or lose files, you can easily recover. And so we're going to be talking about a version control system called GitHub, and they're a company that offers a cloud-based Git repository hosting service. And basically makes it a lot easier for individuals and teams to use Git for version control and collaboration. With FTC, it's super helpful to be able to look at previous code as well as work with other programmers on your team. Think of it as an online backup for all your code. GitHub definitely makes it a lot easier for you to work with and be more collaborative with your team because you can have more people, submitting ideas or posting code that they've worked on. And it's also super helpful for me. Like at least I saw last season that I was working on something and it broke, and I was like, oh no. But then I realized I already did something that actually works pretty well if I refined it. So I found the date that I worked on it, and then I was able to pull up the old code and then finish that off, and it worked perfectly. So that's why it's really helpful. You don't really have to put that much work into getting this to work. So you can go to this page and sign up for GitHub, github.com. It's completely free. And so you're going to see a page like this. Pretty cool. Sign up with a username, an email, and a password. Hit sign up. You'll create a password, do a cool puzzle thing, username, all that. And so we're going to do some basic terminology now. So a repository is a Git repository, or a repo, is a folder that you've told Git to help you track file changes. So in our instance, our folder would be the entire Skystone SDK that we have right here. We can upload this entire thing down there. And that's what we usually do. A branch is an independent line of development. You can think of it as a brand new working directory. And so a lot of companies will have multiple branches, maybe a master branch, which is down here, a beta branch, alpha branches, a bunch of branches testing out different things. So they can all be working on their own with the same code at different times. A fork is a personal copy of another user's repository that lives on your account. And I'm going to talk to you about how to do that with First's official Skystone repository and using clones. A clone is simply a copy of a repository that lives on your computer instead of on a server. To get this, we cloned it off of the GitHub repository that First has. We just gave it to you guys in a zip file. A commit is basically a set of one or more changes to a file or a set of files. Every time you say, it creates a unique identification value or a hash that helps you keep track of the history. And so a commit is pretty similar to an update or a change, and it keeps track of that. And the master is the default development branch. So the master branch is basically the most active branch. It's the highest one. It's usually stable, nothing wrong with it. And so when you're working with FTC, you probably don't really need to use a lot of branches if you're just working by yourself. You can just have your own master branch. So you can actually search Skystone, and then here you can clone or download it, whatever. But what I recommend to do is to do fork it. And fork it, what it does is basically says, okay, I'm going to copy this and make it my own. And why that's important is because then, every time First updates this SDK, you can actually call the update to your fork, and it will update everything without breaking your code. And then when you rerun Android Studio, it will automatically upload it. So the cool thing about it is, or actually before that, we're just going to talk about GitHub Education. So if you want to get more out of GitHub, you can sign up for GitHub Education, which is really cool. And it basically helps students, teachers, and schools access the tools and events that they need to shape the next generation of software development. There are a lot of cool and free things you can experiment and play with on here. You also get GitHub Pro, allowing more options and flexibility in the GitHub environment. You can get free website domains, a website builder, a lot of free cache for different websites. So it's pretty cool to sign up for. And you can sign up here at education.github.com. We're not going to go over sign up because it's kind of tedious because you have to submit school information and all that. But you can do that on your own time, and they respond pretty quickly. So the best part is that there's full support for GitHub and Android Studio. So what you can do is you can download a program called GitHub Desktop made by GitHub. And you can download your repositories to your hard drive. You can just clone them to your hard drive. And then you can, every time you make a change, you can upload and all that. Every time you make a change on another computer and make a commit, you can pull in the new commits. So it's super cool. And so what you can do is you can import your clone/repository or repo into Android Studio, or you can make commits and revisions directly inside. Then all you have to do is, right here, there's going to be a cool button that's basically going to allow you to commit to, if I search up Git, it might come up. Yeah, see, import into version control, share project on GitHub. So since you cloned it, and it's a clone of your repository from GitHub, it will automatically know that and automatically allow you to make commit messages and commit to and make those commits, and then everything gets backed up pretty easily. I did this last year, and it's really cool because all you gotta do is, hit a check mark, write a message, and then it uploads for you. And so you're not gonna also go over the download for this, but here's the link. I'm gonna show it off here while we're at it. So we have, GitHub desktop, pretty easy. You just download it, clone, upload. You can even create repositories from here, so it's pretty cool. And so that's going to be around the end of today and all of our lessons. We went through it pretty quickly today. And we have around 15 minutes left, so we're just going to end out early. If you didn't finish today, you can always head down to stempump.com/r/FTC. And you can read everything that we did today. So we have finished all 3 of our FTC programming camps. We finished web design, Python. Last Friday, we finished our first FTC judging. We have another one of those on Friday. We have Figma design on Thursday. And then next week at the same time, we're going to start teaching Inventor. So if you want to learn how to CAD, your FTC robot or FRC or just learn to CAD in general, you can always sign up for this camp. And that camp also runs for 3 straight weeks like this one at the same time. We also have RPG Maker next week, Java the week after, and then Artificial Intelligence the week after that if you want to dive into more TensorFlow and then learn some Python in the process. You can sign up for more camps here at stempump.com/camps. And also scan this QR code. You can download our app on the App Store, which just got its version 2 update a few days ago, and you'll be able to watch all of the videos that we post for online on here, sign up for online, watch other videos, read any of the courses, anywhere you want. So it's pretty helpful. You can sign up, you can download it using this QR code right here, or go to stempump.com/app. You can find a video of this camp later today or probably tomorrow on our YouTube channel, which is stempump.com/r/YT. And there's also going to be videos of previous camps that we've held, and there's also going to be videos of the upcoming camps that we have. So feel free to add us on social media. Or on Discord, stempump.com/r/Discord, Instagram at STEMpump, and Twitter at STEMpumpTexas or TX. And finally, we'd love to hear your feedback on today's camp because you've been with us for around 3 weeks now, so we'd love to hear how we did. Any new topics you want to be covered, or if you'd be willing to, join up for more FTC programming camps. But other than that, thanks for joining the stream, and have a good week.